Hello everyone, in this video we're going to pick up where we left off in section 13.4 and it's subsection 3, which is approximation by differentials. So theorem 13.4, the sufficient condition for differentiability, what does that tell us? This tells us that you can choose x plus delta x and y plus delta y, that point close enough to the point xy to make epsilon 1 delta x and epsilon 2 delta y insignificant. Remember, what are epsilon 1 delta x and epsilon 2 delta y? That was our in part of our definition for differentiability. So it's this extra stuff here. Okay, so in other words, what does that mean? For small delta x and small delta y, you can approximate the change, right, the increment of z with the differential of z, right? Because remember that delta z is the increment of z and dz is the differential, right? So for small delta x and small delta y, you can approximate the differential with the exact change in z. Right, so we've got this graphic below that kind of explains that, right? So if we look here and I see this is delta y, right? Oops. This is delta y, this is delta x, and this is delta z, right? And then here is dz. So the idea is if delta y and delta x are small, right, then that means that dz is going to go down and dz is going to start looking smaller and it's going to start looking like delta z, right? And when dz starts to look like delta z, that's the idea of the fact that we can approximate dz with delta z, right? So that is kind of a picture representation of what's going on. Okay, so recall that the partial derivatives of z with respect to x and z with respect to y can be interpreted as the slopes on the surface in the x and y directions, right? Remember, this partial derivative was the slope in the x direction, and this partial derivative was the slope in the y direction. So what does this mean? This means that dz, remember dz is our differential. Our differential is equal to my partial derivative of x times delta x plus my partial derivative, this is supposed to say with respect to y, this is dy, delta y. So this means that that differential that looks like that represents the change in height of a plane that is tangent to the surface at the point x, y, and f of x, y. Right? Because a plane in space is represented by a linear equation in variables x, y, and z, right? We'd have like 3x plus 4y plus 7z equals to 1, right? That's an equation of a plane. Because it's everybody's to the first power there, sometimes or oftentimes we call the approximation of delta z by the differential dz a linear approximation, right? Okay, so what we're going to do now is use the differential dz to approximate the change in z, right? To approximate the change in z, that is delta z, as xy moves from the point 1, 1 to the point 1.01, 0.97, and compare this approximation with the exact change in z, right? Again, the exact change in z is delta z. Okay. So the first thing we want to do here is find the partial derivative of z with respect to x, right? And the partial derivative of z with respect to y. Because what we're going to do here is find the differential, and then we will show how close that is to the actual delta z, which we can find, right? So the partial derivative of z with respect to x is going to be, well, this is z, right? Z is this guy right here. So we would need to do the chain rule, right? So I do 1/2 and then 4 minus x squared minus y squared to the negative 1/2, and then now we chain on the derivative of x, which would be 2x. Oh, sorry, minus 2x, right? So rewriting that and canceling things out, I end up getting minus x over top of the square root of 4 minus x squared minus y squared. It's my partial derivative. And now if I take the partial derivative with respect to y, I end up getting 1/2 4 minus x squared minus y squared to the negative 1/2 times negative 2y this time, which is negative y over top of the square root of 4 minus x squared minus y squared, right? Okay, so now that we have those partial derivatives, we can answer the first part of the question. We can use the differential dz to approximate our change, right? Because the idea is that we can find dz by this formula up here, and then that's going to be a really good estimation for what delta z is. Okay, so what we're going to do is we're going to let our point xy be the point 1, 1, and the point x plus delta x and y plus delta y equal to that new point 1.01 and 0.97. What does that mean? That means that my delta x, well, if x is equal to 1 and x plus delta x equals 1.01, delta x equals 1.01, and delta y equals to, if I'm going from 1 to 0.97, it would be negative 0.3, right? So the change in z, i.e. delta z, can be approximated by the differential and the differential is dz. It's given by that formula right up here, right? So dz, which is equal to delta z over delta x plus delta z over delta y, which is negative x over the square root of 4 minus x squared minus y squared. Delta x is 0.1, and then plus, and then we do negative y over 4 minus y squared, or minus x squared minus y squared, and then negative 0.0, or negative 0. Oops, that should be 0.3, shouldn't it? 0.3. Okay, so what point were we looking at? At the point, we were looking at the point 1, 1. So at the point 1, 1, we get that x equals 1 and y equals 1. So dz, if we plug in x equals 1 and y equals 1, I end up getting negative 1 square root of 1 minus, or 4 minus 1 squared minus 1 squared, 0.01 plus negative 1, 4 minus 1 squared minus 1 squared, negative 0.03, which equals to 0.0141, right? So again, that's what my differential is, and the whole idea is that this is going to be approximately what my change in z is, right? It's going to be a good estimation for my delta z. So now let's find what delta z is. We can find delta z because we know the formula for delta z, right? The exact change which is delta z, is, remember our formula for delta z, and again, what point are we at? We're at the point, our formula for delta z all the way back up is this guy, right? But we plug in our delta x, we plug in our delta y, and our x and y, right? So in general, this formula looks like f of x plus delta x, y plus delta y, minus f of xy. But in this case, we get f of x plus delta x, that's the 1.01, and then the 0.97 minus the f of 1, right? So if we go to the function, which is in orange there, and I plug in both of those values, I end up getting, scooch it over a little bit, right? I plug in 1.01 and 0.97 into this equation, into my f of x, and I plug in 1 and 1 into there, and I end up getting 0. Wow, I don't know what happened there. 0.0137, right? So that's my delta z. And if you notice, they are pretty close. So the idea is that, again, that delta c is approximately equal to my differential. And as you can see there, that we're getting that, right? They're pretty close to each other. Okay, so now let's talk about theorem 13.7. So remember, we talked about, it was actually in theorem 13.4, the sufficient condition. So if I have a function of two variables, if their partial derivatives are continuous, then it's all differentiable, right? And so theorem 13.5 tells us that if a function is differentiable, then it's continuous, right? Just because just because my partial derivatives exist does not mean that I am that my derivative or that I'm differentiable, right? So just because my derivatives exist does not mean I'm differentiable. However, if I'm differentiable, then it means that I'm continuous, right? So there's two different things there. So what we're going to do in this next example is we're going to show that for this example, my partial derivatives exist and that I'm not differentiable, right? That's the idea. Or this is going to be like kind of like a counterexample to show what I keep saying, that just because they exist doesn't mean I'm actually differentiable there. Okay, so to show that my function f of xy is not differentiable, because that's the idea, we're going to show that it's not differentiable, and we're going to show that these exist, right? So to show that f of xy is not differentiable at the point 0, 0, we will show that f of xy is not continuous at 0, 0. Because if it's not continuous, that was 13.4, right? 13.4 says if they're not continuous, then it's not differentiable, right? So we're going to show that f of x is not continuous at 0, 0, therefore it is not differentiable, right? Okay, so how do we show that it's not continuous? To show that f of xy is not continuous at the point 0, 0, what are we going to do? We will look at values of f of xy, or outputs, along two different paths. Right? Because remember, in order for a function to be continuous, at a two-sided function to be continuous, so if f of xy is continuous at at a point x naught, y naught, we must have that the limit as xy approaches x naught, y naught of f of xy has to equal to the function value there, right? We learned that in last section. In order to be continuous, the limit has to be equal to the function value. So what we're going to do is show that if we look at a limit along one path, it'll give you one function value, but on a different path, say the purple path, it gives you a different function value. That means that this limit does not exist, right? It doesn't equal to the function value because the two sides, or the limit from two different paths does not exist, right? So if the limit does not exist, then we can't have this equality, and therefore it's not continuous. So we look at limits, we show two different paths, give two different limits, therefore the limit does not exist, therefore it's not continuous, right? So we look along two different paths and to the point 0, 0, right? Because we're headed towards 0, 0, right? So in this case, I guess I should put 0, 0 here because we're plugging in 0, 0 and f of 0, 0. Right? Okay, so what's the first path we're going to look? Again, this is kind of the same idea. We looked at paths, the idea of paths before, but we look for a path that allows something good to happen, right? Some good paths are along like the x-axis. Some good paths are on the y-axis. Other ones are along the lines like y equals x. So that's what we're going to look at here. So along the line y equals x, my function values, f of x, y, well, I'm not plugging x, y, I'm plugging x, x in because y is equal to x. And if I plugged in x, x, remember, we're not equal to 0, 0. We're heading towards 0, 0. So I plug it into this function, the top function here. So if I plugged in x in for x and x in for y, I'd get minus 3x squared over top of x squared plus x squared, which is 2x squared, which is minus 3 halves, right? So what does that mean? That means the limit as x, x, remember that's our way of saying along the path y equals x. So as I approach 0, 0 with my function, well, my function is equal to the constant 3 halves, right? So I get the limit as x, x approaches 0, 0 of negative 3 halves, because that's what my function looks like along that path. There's nowhere to plug in 0, 0, so this limit is negative 3 halves. Oops. So now let's look along a different path. So along path 2, this time let's do along the line y equals negative x. So this time if I'm along y equals negative x, then my function f of x, y is no longer xy, it's x negative x because y is equal to negative x. And now if I do this, again I plug it into that first function, I would plug in x for x and then I plug in negative x in for y. If I did that, my negative sides cancel out with each other, and I have an x squared, right? So this looks like positive 3x squared over top of 2x squared. So this time I get positive 3 halves. So that means that my limit along that path, which is x, negative x, as I approach 0, 0 of my function, well, my function along that path is just the constant negative, or positive, this time positive 3 halves. So I have nowhere to plug anything in, so it's 3 halves. So on one path, it equals to 3 halves. On the other path, it equals to negative 3 halves. So my limit, in general, cannot exist, right? So the limit as or I'll say the limit of f of xy as xy approaches 0, 0. Remember, this is like the limit from every direction, does not exist, right? Because from two different paths, two different directions, we showed that they're not equal, right? So the limit does not exist. So because the limit does not exist, it's not continuous. At 0, 0. If it's not continuous, then it can't be differentiable. So we show that it's not differentiable, right? So f of xy is not differentiable at 0, 0. Cool, so we proved the first part. The idea is we showed that it's not differentiable even though the two partial derivatives do exist, right? So now let's show that the two partial derivatives do exist, right? So on the other hand, by the definition of partial derivatives, f of x, the partial derivative with respect to x, and f of y, shouldn't have put a comma there, you have, so remember what were the definitions? Remember it was like the f of x plus h, but in this case, since it was partial derivatives, we only had the x getting messed with, right? So if I look at f of x at the point 0, 0, or the partial derivative at 0, 0, using the definition of a partial derivative, it looks like the derivative as delta x approaches whatever's x there. In this case, it's 0. And then it looked like f of x plus delta x, but in this case, what is x? My point we're focused on is 0, so that is just delta x there because it's x plus, so 0 plus, I could maybe write 0 plus delta x, and then what is, remember y gets left alone because this is the partial derivative with respect to y, so this is y, but y is 0, and then it's over delta x, right? This equals to, well, if I plugged in delta x and 0 into my function, I would get, if I plugged in delta x into here, I'd end up getting 0. If I plugged in actually equal to 0, 0, then I would get 0 because that's what the function is, right? So here, I end up getting, oops, and I was supposed to put, remember it's f of x plus h minus f of x, so I should have put minus f of 0, 0, right? Because 0, 0, it's minus f of xy, but it's 0. This is x plus delta x, y, right? Remember, these are the definitions. So now this guy is the limit as delta x approaches 0, and oops, pull this all, I can get it all in there. There we go. Scooch that over. This looks like if I plugged in delta x 0 into there, I'd get 0. If I plugged in 0, 0, f of 0, 0 at the point 0, 0, it's equal to 0. That's what I was trying to say earlier. So I get 0. So 0 minus 0 over delta x, well, that's just 0 over delta x. So no matter what the limit is, this is just 0, right? So it exists. Now when I do the same thing for y, it looks like the limit as delta y approaches 0 of f of, this time x is 0, and then it's y plus delta y, so that would be 0 plus delta y, right? Because remember it's f of x y plus delta y, and then it's minus f of x, but, or f of x y, but in this case x and y, we're looking at the point 0, 0 over delta y, and the same thing happens. I end up getting, oops, 0 for when I plug in 0 and delta y into there, and then I get 0 because the function value at 0, 0 is 0 over delta y. And again, even though delta y is going to 0, the numerator is 0, so it's just the constant 0, so we're good, right? So we showed that the partial derivatives exist and equal to 0. So the partial derivatives exist and equal 0 at the point 0, 0. Right? So even though the partial derivatives do exist at the point 0, 0, it's not differentiable. So this is a nice like counterexample as to why we actually do need it to be continuous at a point in order for it to be, that's sufficient in order for it to be differentiable. All right, that's all I have for this video. Thank you.